In any event, this is lecture 29, hopefully February 12th, 2014, and today we're going to talk about information theory. We haven't done that yet, but we're going to do that finally today. In particular, we're going to talk about, well, we're going to continue our discussion of universal compression, and we're going to leave that discussion with maybe the depressing conclusion that there doesn't seem, at least from the analysis that we have done, we will have done at that point, there won't seem to be any sort of way of actually using this for any practical application, but then we'll be, in some sense, saved by the Lempel Ziv compression, which is what we will be talking about for the remainder of today and also for the beginning of next lecture. So, again, you should be reading chapter 14 in our book. And I actually forgot in our reading to add the reading on Lempel Ziv compression. I believe it is one section of one chapter. So you should read that because I think it's worth, we're going to actually go through the proofs in some detail of this one because it's just a fairly remarkable discussion and argument to show that something which is purely algorithmic, an algorithm that's just purely algorithmic, in fact, and doesn't use the probabilities, as we will see, can be provably shown to converge to the entropy rate of the stochastic process, even though we're not doing anything with probabilities. And it's, in some sense, just a seemingly heuristic procedure for doing compression. And it seems to be a good heuristic as well when we talk about it. But in any event, do read that chapter. Again, there's no outstanding homework, but I do hope that will change soon. I do want to have a couple more homeworks this term. There's no class on Monday, just to remind everybody, because of a holiday. I think it's President's Day, or is it? I think it's President's Day. Is that right? Okay. It used to be back in ancient times. It used to be George Washington Day or something, and then there was Abe Lincoln's Day, but then they merged them together. It's called conservation of holidays. Final presentations. You do have a deadline on Monday. One of you have emailed, and I think I owe you an email, right? So I think we'll email back and forth about that. But remember, the other thing to remember about Monday's deadline is that it's not binding. The idea of Monday is really to force you to send me an email, but a well-qualified email and well-researched email and a well-understood email and an email that demonstrates that you've done, to me, that you've done a lot of work. But what really it is it's an email. So as long as I've seen that you've done a lot of work and trying to find something, then that's fine. But don't take the deadline lightly. Like I said, I mean it's an attempt to sort of force you to contact me with what you've been thinking about and what papers, abstracts you've been reading and what kinds of things you're thinking about. Although you're free to contact me by email before, as a few of you have. So. Okay, any questions on these milestone deadlines? Okay, let's do a little bit of review. So remember we had the definition of the Kolmogorov complexity, and as we talked about last time, it corresponded to, according to a universal computer, the shortest program that both halts and generates the string x. And we had this result, which followed from Kraft's inequality, that when we sum over all programs that halt and we take 2 to the negative the length of that program, well, that's a number that lies between 0 and 1, and we're just going to define that number to be omega. Okay. And that's a number that we saw had some very interesting properties. But first of all, we had these somewhat more mechanical, but actually very important theorems, which I want to remind everybody about today. Again, at least just their definition. The first one sort of says when you do have a random source, like a random Bernoulli sequence of Bernoulli random variables. So it's important to understand what this actually means. So where's the randomness? So the randomness is here, right? Is this bit? Right? That's a random vector, and we're taking the Kolmogorov complexity of that random vector. So it's a random Kolmogorov complexity. Right? So the value is just a number, which is a length. Right? It's a program length, which is an integer. So the probability comes from the bit that's highlighted in yellow, but it's a function of a random variable. computed via the Kolmogorov complexity, and we're asking what its probability is, namely the probability of being k less than 0 compression. So 0 compression would mean essentially something like storing the string, which is of length n. And what this is saying is that the probability of it being k less than 0 compression is exponential in k. So that means that you're not likely, or you're exceedingly unlikely, you're exponentially unlikely in terms of the number of bits of compression that you're going to get from some random string on average, or at least according to the probability, to actually get k bits of compression. Okay. So the statement of the theorem is clear. So this is sort of intuitively what we would expect, right, as well, because it's saying that there just aren't enough short programs to go on. Most programs, any string that's long, that's also simple, must by definition have a short program, and there aren't enough of them. So most long strings are complex. And so we define the notion of algorithmically random by saying, okay, well, if you have a sequence of strings or a set of prefixes of strings, that that string is algorithmically random if it's the case that it ultimately can't be compressed. And we gave it the example of, if we had a bunch of coin flips, there is some chance that we're going to have a bunch of zeros at the beginning. That's very, very improbable, but it's certainly possible. But it becomes less and less possible, or less and less probable as n gets bigger and bigger. At some point, you're going to have to, if it's a fair coin, you're going to be seeing some ones and zeros. It just becomes exceedingly improbable very, very fast. And so that becomes algorithmically incompressible. So it's a random. So our notion of fair coin flips are going to be algorithmically random, but then on the other hand, there might be some other algorithm, or actually there can't be an algorithm, right, that generates it, because even like a pseudo-random number generator, which are the things that we use to initialize our random starts of our systems in our simulations run on computer, those are really not even close to random because they're extraordinarily compressible by the program that we use to generate the random number sequence. So just by definition of having a program that's short, that you want to fit in memory, that generates random numbers, means that it's very, very not random, algorithmically. So next time you write a paper and you say, we used random initial weights, say, we used pseudo-random initial weights. We didn't really, it's because we don't use random initial weights. We don't do that. Unless somehow you have a sensor which detects, like, for example, very, very precisely the average number of photons bouncing off something. There are ways that you can maybe get better estimates of random numbers, but on the other hand, I'm going to emphasize again in the review section today, is nature really random? So, in this sense. So, the next definition is similar, and it says that a string of an infinite length is algorithmically compressible if this ratio goes to 1. Now remember, we had this upper bound of the Kolmogorov complexity, the length conditional Kolmogorov complexity, which was basically, the Kolmogorov complexity was upper bounded by the length conditional plus like log star n plus a constant. Right? So log star n over n is going to go to 0. Right? And then the constant over n is going to go to 0. So we bound it in terms of this, right? So you're conditioning on the length. And that doesn't really change anything. So obviously if this is true, then the Kolmogorov, since this is an upper, so since that plus some other stuff that goes to 0 is an upper bound of the Kolmogorov complexity unconditionally, the Kolmogorov complexity is also going to go to 1 if the string is algorithmically incompressible. So right, so it's kind of like saying, I guess this is true. Right? Basically, the length conditional Kolmogorov complexity basically says you have to store the string eventually. Here's the proof. We're not going through the proofs what we did last time, but I just want to restate the theorem. Another example is again when you have a sequence of random variables, taking the sort of per symbol Kolmogorov complexity. So remember, what is this? This guy here, again, this is a random variable, it's a random vector. And then this quantity is the random function of a random vector. And we're taking, and this makes it an expected per symbol Kolmogorov complexity, saying that quantity converges in probability to the entropy of the count of number of ones, the relative number of ones in the string. or actually, which is the same in this particular case as the Bernoulli probability, obviously. So many of these relationships that we've seen relate the Kolmogorov complexity and the entropy when there is a random source. So, like for example, in this particular case, we have a random sequence which is governed by some probability distribution, some random process. And so the Kolmogorov complexity itself becomes a random variable, which we then can sort of think of as a coding length of a random string. Any string that comes in that we get, we use k to code it, and then we take the n, and this is sort of like an average. So this is like a weak law of large numbers thing. And we saw also last time, I can't remember if I have this theorem again, that the Kolmogorov complexity is just as good, is no better or no worse asymptotically as the Shannon length for such random strings, 1 log of 1 over p. So we're not beating Shannon. But on the other hand, we have this discrepancy, and this is what this slide is all about, remember, which is that it seems that for many strings, or for certain strings, for strings that are somehow structured, the coding length is not very good when we use 1 over p of x, because p of x is blind to the contents of x. P of x is only based on the probability of that string, not its contents. And so when we have a string consisting of all zeros, like this guy, or a string which can only be described by listing the string, which I don't even do here, as I said last time, and if those strings are given equal probability, they have the same number of bits. And so, asymptotically, it's saying that there just aren't enough simple strings. And so why does this not matter asymptotically? Well, yes, for any finite length, you might get a bit better compression if you were to use, for example, the Kolmogorov complexity to give us the coding lengths. Why? Because, there are going to be some strings that are easier to describe, like the all zero string. You can just say print n zeros. That's a lot easier than writing out n zeros and having like a code word with n zeros in it or something. But asymptotically, and this is the intuition as to why the discrepancy doesn't matter asymptotically, is because, remember, as n gets bigger and bigger and bigger, there are just going to be fewer and fewer, relatively speaking, number of such simple strings, right? Because remember, the Kolmogorov complexity, the probability, according to all of these other things, it's very unlikely that we're going to see long strings that have short programs, just because there aren't enough short programs for all of those long strings. And so we're going to have exponentially many more. So all of these simple strings are going to become a tiny sliver of the probability space. And relatively speaking, these simple strings end up not counting in the probability from the probability perspective. So, on the other hand, this is where we sort of saw the philosophical aspect of this material, which was, we look around our world, and I give fractals as an example, and fractals were, and I think still are, very excited as a way of describing nature, because there's so many different real-world objects, from trees, from coastlines, from mountain ranges, from neural fibers from the human brain, from structures of materials down at the microscopic level. There's so many materials that seem to have sort of this self-similar fractal dimension, all of which are described by, can be described, or you can actually come up with algorithms that mimic them very, very closely. And maybe with slightly more elaborate algorithms, maybe we don't actually have the exact algorithms which will produce an exact coastline, but maybe with slightly more elaborate algorithms, or only slightly more, we could describe very accurately something that would produce a perfect mountain range. Occam's razor says, well, why, what might we believe? So Occam's razor says that when we're looking for an explanation of a phenomenon, of any phenomenon, we're interested in finding the one that's most simple, all other things being equal. So if we have two explanations of something, both of which fit perfectly well, but one of which is simpler by some measure, and another which is less simple by the same measure, we choose the one that's simpler. because it seems to be more probable. So this gives us a prior probability of strings. Now consider the list of all possible halting programs. So let's say we have a probability distribution over all halting programs. So if we were, for example, to sort of take a uniform distribution over bit strings, just uniformly at random, okay? But what we're taking uniformly at random over is the programs, right? So some of them are going to halt, some of them are not going to halt, some of them are not going to be programs, right? But we're going to just strip away the ones that don't halt, right? And that's, because that's just something that makes sense to talk about programs that halt, and also because we can't solve the halting problem. So we strip away the ones that don't halt. We have left with all of these halting programs. So when we have this uniform distribution over bit strings, over arbitrary length, the short programs are going to have higher probability. So this is a prior probability on programs starting from a uniform probability over bit strings. So we're not starting with any biases on the probability of these bit strings. We're starting from uniformity on bit strings, where the bit strings correspond to the programs. Okay, so this is in some sense, a very weak prior. At least on the programs. We're putting a weak prior on the programs. We're saying, well, short programs are more likely, right? Because it's much more probable under a uniform distribution over bit strings than amongst the ones that are halting. The ones that are short are going to be much more probable, exponentially more probable, in fact, than the long ones. Okay. And thanks to Kraft's inequality, to the unaccountable, and we have this fantastic result from Kraft, which I'm sure he never realized would be as philosophically important, but it says that this is a valid probability distribution over programs. So, I mean, it's in some sense an assumed fundamental property of nature, but it gets into sort of some very deep concepts, because we're not really saying much about nature other than that it's uniformly at random, and we're giving this probability over programs, which induces this higher probability for short programs. But then once we have a higher probability over short programs, what do those short programs make? Those short programs might make long strings that are very simple, right? Like coastlines and trees and brains, and so they produce simple strings. The more starting from uniformly at random over bit strings that produce programs, the consequence, when these programs are still given random input, the programs take random input and then are going to, because they're short programs, they're going to produce strings which are by definition simple because they come from a short description length. And so we can then talk about the universal probability of a string is by summing up over all programs that produce that string. And obviously the short programs are going to be the major contributors to this overall probability. So this is the other thing that I really didn't emphasize this strongly enough last time. So it's the probability that a fair coin flip will produce programs to print out X. So remember, we're starting, again, from just perfectly uniformly at random, but then we're producing in this sort of one level of indirection, or once removed fashion, something which produces strings that can be very, very highly structured and very simple, only because it's the programs that are short that are highly probable. Not necessarily, we don't have a uniform distribution of the objects that we see. We have a uniform distribution over the things that generate the objects that we see. So simple strings under this probability distribution are much more probable. And what do we get with simple? What are some simple strings? Well, this is where fractals come into play. So with short programs, we can generate very interesting fractal images. Like some of these guys. I sort of encourage everybody to read Benoit Mandelbrot's book. I mean, where like for example, these are some very simply generated fractals, and you sort of recursively apply this transformation to a set of shapes. And what we get is something that effectively has an infinite length. it's sort of it seems like it's a contradiction. And no matter how far you zoom in, you keep getting more and more length. But what you end up getting is something that's very similar to a coastline, which again, in some sense, you could think of as having infinite length, because the shorter the yardstick, or the shorter the stick you use to measure the length of the coastline, the longer the coastline gets. If I use straight lines of a mile long or straight lines of a half mile long, I'm going to get a longer coastal circumferential length with the half mile long stick than with a 1 mile long stick, and so on and so forth. So that's the notion. And so these things can then be generated. These types of things can be generated by these very simple programs. I mean, here's a program that generates symmetric. This stuff here generates symmetric coastlines of various kinds, but it's not too much to add a little bit of variation to generate things that produce islands, like the island of North and South America. Sorry, that's not an island. But I just want to interject a little bit of humor into this discussion. So, I mean, on the one hand, we're looking at these are just images that are generated by these simple algorithms that humans have come up with over the past, 20 years or something. But, these algorithms, it doesn't take much more sophistication. These might, in some sense, and what I meant by this last comment is that, these are really, in some sense, mundane, because these are programs that just run on a computer that we can, stick in our pockets these days. But, what if the computer was this parallel computer of the laws of physics? So then short programs run using the laws of physics could produce things that, still have fractal-like structure, but are maybe slightly more realistic, like the images that we see around us. So I guess, the idea, this is one idea of looking at it, is that the universe was instantiated with the laws of physics correspond, and so there could have been lots of ways of instantiating the universe. The universe is basically being generated by a short program. So the universe originally had there was a uniform probability over random bits, but because short programs were more likely, a short program won. And so what we're seeing in the universe, or structure we're seeing in the universe, is the result of this short program generating lots of stuff, starting from random input. And what this idea, and I think fractals, in some sense, seems to be consistent with this philosophical idea, is that what we're seeing is really still randomness, but it's really being caused by these higher probability short programs being fed random input. So, okay. I should have some music here, right? Are you catching my drift a little bit? This is not to say anything theistically. I'm not meaning to imply anything in that sense, but I am just saying that from the mathematical description of these objects and from our description of Kolmogorov complexity, this seems to be kind of an intriguing idea. Now we sort of, that was the philosophy. The question is, now we're getting back to some of the more practical matters and maybe some of the depressing aspects of Kolmogorov complexity, which is the generation, the computing of the Kolmogorov complexity. Because, hey, it would be great to be able to compute this, but we can't, because we can't solve the halting problem. So while we know that the Kolmogorov complexity exists, and we know that omega exists, we can't run a halting program. It just doesn't. And then we proved that last time by creating a contradiction. And that's also true of this number omega. So omega isn't computable. So it exists. We know it exists. We know it lies between 0 and 1, but we can't get it. And the interesting thing is that if we could get it, we saw last time that we can solve all of these amazing problems, because essentially we can solve the halting problem. And with the halting problem, we can just sort of create a program to search forever until it stops. Search all possibilities until it stops. And then if we can tell if that program halts, we can solve that. We say, oh, look, it found a solution. So we can answer any yes-no question with omega by writing a program, searching all possible solutions, We don't even have to run the program, just feed it to H, and if H returns 1, then oh, it halts, it found a solution. So the answer, there must be a solution. And usually the yes-no part of a question is the hardest part. This is related to the theory of NP-completeness. In all of these NP-complete problems, asking whether or not there exists a satisfying assignment for 3-sat is the difficult part of finding a satisfying assignment for 3-sat. And there are ways. In polynomial time, you can just call the yes-no thing multiple times. But getting the yes-no thing is the hard part. So this is also similar. It'll answer any yes-no question. If you haven't taken a class on computational complexity theory, then I suggest doing so. I think everyone who does anyone who goes near a computer should take a class on computer science theory. So have you been within 3 feet of a computer in the past day? If you have, take a class on computational complexity theory. It's absolutely essential. Okay, so then the next thing we had is this universal probability of a string, according to this philosophy. And here's the definition. So this is actually, I think, new stuff now. We didn't go this last time. But how did you like that review? That was a nice review. It was, in some sense, a better review than last lecture. I wasn't happy with the outcome of last lecture, to be honest with you. And I shouldn't put this on YouTube, but those of you who are listening to this on YouTube 100 years from now will now be curious about the last lecture and go back and listen to the poorly done last lecture. Okay, so back to what I've just highlighted in yellow. That's the universal probability of the string, which is lower bounded by P star, where P star is the true minimum. So P star is the program that achieves, is the program that gives you the value. It's the program whose length is the Kolmogorov complexity of the string. Okay, so that basically then gives us this. So we have this lower bound of the probability. And so we, in fact, very simply have this sort of sandwich bound, where the probability is lower bounded by 2 to the negative k and upper bounded by some constant times 2 to the k. And the reason is because of Kraft's inequality. And with this, then, what we can get is this sort of sandwich bound with respect to the Kolmogorov complexity. So basically, it's saying that the Shannon lengths with respect to this universal probability is roughly equivalent to the Kolmogorov complexity. Okay. That's when we use this universal probability of strings.
So what does that constant depends on when the length of the string gets larger and larger?
Yeah, it depends on all of this other stuff. Basically, you take the shortest one, and then all of the other stuff in the sum that achieves the string becomes a constant, right? Because it's upper bounded by 1, right? And so that's just a constant. The point is that it's just a constant. Then we solve it, so this is like log. We take the log of both sides, and we solve and get a constant. The important thing is, like, if we divide by n, the average length is going to be like it's the entropy in the middle, which is going to be sandwiched by the Kolmogorov complexity, and can be as close as we want as the Kolmogorov complexity. We've got an upper and a lower bound, so it's really tight, and asymptotically tight. Thank you for asking that question. I like getting questions because it makes us understand things better, including me. So then we can actually compute the entropy. The entropy of this distribution is E of k of x, where x is a random variable. It's a random string drawn according to this universal probability. So this entropy then really, in some sense, is the universal entropy, the universal complexity of the universe, in some sense, according to this Occam's razor philosophy. Now, what do you think? Is this a reasonable philosophy? Is this something that you believe?
It's tricky.
It's tricky. In the field of machine learning, for example, the whole notion of regularization or Bayesian prior is exactly similar to this, where you're trying, in some sense, based on or either a regularizer or a Bayesian prior, to sort of, without any other knowledge, all other things being equal, choose the thing that sort of matches that prior, where that prior is something that gives better score to simpler things, where the prior is the thing that determines what simple means. All regularizers have a preference, and what they preference things towards is that which it says is simple. So sparse priors would say, for example, the number of coefficients are 0. Is that simple? If that's the regularizer, if that's your assumption, that's simple, and yes. A Kolmogorov complexity prior would say that the set of coefficients has to be easily describable by some short program. There are many different possible ways of doing this, but in each one essentially is a different notion of simplicity. Yeah.
Is there another issue with what you choose to be your features? Like maybe it's true that in machine learning, the problems we try and solve, or the problems we're interested in, happen to also be ones that we have features that discriminate well for, and that maybe there are many other things in the universe that we're not interested in, but those things have no short or no good features, no small set of good features.
I'm not sure I understand the question exactly.
Like if you're trying to classify, is this apple or banana, then color is a good feature for that. And color happens to be something that we as humans use a lot because it's meaningful for things that we care about, which is like which fruit to pick. But if you just pulled a random problem out that wasn't biased by things that we're interested in, is it going to be true that there is a short or a small set of features that's useful in discriminating on that random problem?
That's hard to say. My feeling, this is maybe seen as a philosophical question as well, is that if there is structure, I always thought that you could instantiate, and actually, if you remember last quarter's problem set, if you can instantiate a universe which is very, very low entropy, but is still but looks random, entirely random to us. So pseudo-random number generators are a good example. So these are deterministic sequences, but they appear random to us. But you could take a random number generator that generates full-length feature movies that to us just looks like noise, like static on a television set. But in fact, there can be extraordinary correlations and extraordinary compression abilities. It could be the case that the pixel at coordinate ij at time frame t is always exactly the same pixel at coordinate t prime at coordinate I prime j prime at time t prime, where t prime is arbitrarily far away from t. These kinds of temporal and spatial distal correlations generally tend not to exist in our universe. And so if there was some pattern, if you had this pattern, which is really, color is just some pattern in some description of the universe, some description of some physical phenomena. That's what the color yellow is. If you had the right pattern in this crazy universe, and you say that pattern, that crazy, what from our perspective would be very, very sparse and arbitrary and random pattern, that pattern would be very useful. And that might inspire in some alien species the notion of yellowness, whereas to us it's not even perceivable, because the durations over which correlation exists might be over 1 million years, and it's not over more than a lifetime. I think we actually are beginning in the past 20 years to exploit that phenomenon by introducing, one of the reasons, we haven't talked about this, but low-density parity check codes and turbo codes and modern sparse coding techniques introduce correlations in signals that tend not to occur in nature. And one of the reasons why they work well is because decoding can then exploit, by knowing the pattern of correlations that were introduced at the encoding side, the decoder can exploit those correlations, and those tend not to be corrupted by nature, because nature tends not to have those patterns of correlation. Nature tends to be spatially and temporally local in terms of its patterns of correlation. So I think the answer to your question is yes, there would be. as long as there's structure. Now, if it was a completely random, uniformly random universe, if it wasn't, then no, there wouldn't be. There'd be nothing you could do. But then the question is, would anything be around in such a universe that would want to do that? I mean, by our very desire to want to do that means that it's a structured universe. So, but that doesn't mean that a different universe could have beings that would be interpreted as just random noise to us. And forget about communication. I mean, just forget it. It'd just be random noise. It would never be anywhere, even though they could be, in some sense, from the perspective of their properties, with a different instantiation, a different program that happened at the time of the Big Bang. They could be just as conscious and sentient as we are. So that's again very philosophical. So I apologize for getting off on this tangent. So what we want to do, let's just review what we've got. Okay, this is a review of last lecture and a little bit of this lecture. So the complexity of a string is the length of the shortest program that can generate X when run on a universal computer. It's an algorithmic definition, and strings whose shortest program length are as long as the string itself are called algorithmically random. That's the assertion. We can think of many structures in the universe as arising this way. So this is the notion of Occam's razor, and this notion says, under a uniform probability, are more probable over bit string programs. So that we can say that under a uniform prob of program so we don't, it's a very sort of weak notion of implying probability. The only probability is that there's rules, and then randomness gets fed to the rules, and the rules, by it being program, the rules are essentially programmed sort of produce structure by there being rules. And so the short programs are then more probable according to some length. And then this, for example, can be used to give us the universal probability of the string X, which is not computable because of the halting problem. And we also have this number omega, which if it was available would be an oracle. So we can't compute oracle, we can't compute it, but we know it exists, and then we can deduce that it's incompressible. I think I reviewed that there. So even though it exists, even though we can't compute it, we can study properties about it. That's a very interesting common thing that happens in mathematics, where you can study properties of objects which we know exist, but we can never actually achieve. Even though K is incomputable, we've related it to entropy in many ways. And so that's good news in some sense, I think, for entropy. But on the other hand, it begs another question. It's not practical, right? So we can't actually compute it, we can't use it. And maybe for any finite block length, maybe we would do a better job with using the Kolmogorov complexity rather than using 1/log of p of x bits when x is all zeros, we want to use something much more sensible. So the question that we want to ask is, are there any other purely algorithmic forms of compression besides the Kolmogorov complexity that can be shown to relate to the entropy? And ideally that can be used to compress down to the entropy rate. And what we mean by algorithmic is that we don't need to explicitly refer to the probability distribution governing symbols. Like, for example, the Kolmogorov complexity, if we could compute it, every time we get a string, we would just send its shortest program. Right? That doesn't have anything to do with the probabilities. And we know, what we've proven, is that would give us the entropy rate. Right? What a great compression scheme that would be, if we could somehow do it. But the question is that that's not practical, so the question is, are there any practical schemes? Are there any algorithms that do not use the probability distribution but still give us the entropy rate? So let's just briefly review our compression algorithms that we've studied so far, all of which we've proven converge to the entropy rate. So we have these fixed number of source symbols. This is the discrete alphabet case. And we have fixed length block codes and fixed length code words. And we recently proved that we can compress down to the entropy rate, but no further. And that was Shannon's original theorem, and the way we proved that was with the method of types or with the asymptotic equipetition property. And that's not a practical coding scheme, because that basically means we need to sort of enumerate all of the typical sequences. And there's only a relatively small number of typical sequences. We need to know the probability distribution. We need to know the entropy at least. So it's good for proving the existence of codes, but it's not practical. We talked about symbol codes. So it's variable length code words for each source symbol. So more probable symbols obviously should have longer codes. And an example of this is Huffman codes, right? So very, very improbable symbols have a long bit string, according to Huffman, and very, very probable ones have short bit strings, and Huffman is optimal. We need a distribution. In order to compute a Huffman code, we need to know the probability distribution. And if we don't actually have the probability distribution, we pay a penalty. And remember the penalty, if we use Q and the true distribution is P, is the Kullback-Leibler divergence between P and Q, which is given by this. This is review. So this should be very familiar to everybody. And then moreover, even if the symbols are independent, in order to achieve the entropy rate, we need to code blocks. And that's because most distributions are not dyadic. And in order to, we get this one bit per symbol bit penalty. And in order for that to not really cost anything, we need to encode, blocks of symbols. And that also relates to the typicality theory as well. And then stream codes, remember arithmetic coding was another interesting method of coding. We don't, in this particular case, necessarily emit bits for every symbol, but we might wait for a while, and then only at some point when we're sure that the probability lies within a particular, uniquely specified range, do we say, okay, let's emit more bits to sort of designate that range, and then we keep making the range smaller and smaller and smaller, and as soon as the range becomes uniquely known, we emit more bits to sort of narrow the range even further. That's the idea of arithmetic coding. And we don't need fixed blocking. It's a pretty neat coding idea. Like we don't need to sort of say, okay, thou shalt have block sizes of k at the beginning of the coding stream. That doesn't need to happen with arithmetic coding. And you can also, in stream coding, start very quickly. You can start coding very quickly, and you can moreover start decoding very quickly, which we said was very important for streaming applications, like streaming Netflix video, which is the most important consequence of information theory, so that you can watch episodes of House of Cards without having to wait for an hour. Right? Does anyone get that? What is House of Cards? I don't know what that is. I just made that up. It's just some random sequence of 3 words. Netflix is also a random syllable. Okay, so what else do we have? By the way, I just realized that Google, with their amazing speech recognition capabilities, will probably someday run speech recognition on this entire lecture series, and we'll be able to parse and search through everything that I've said here. So. Someday they'll search for House of Cards, and this lecture will pop up and say, what does this lecture have to do with House of Cards? And they'll be perplexed and confused. So we could just start saying random things. What's another thing I should say? Get Google to index. Give me some.
I think, did it already do that for one of your lectures? Do the transcript?
Did it? I don't know.
I think I kind of remember clicking on the thing and
seeing the words?
Yeah, a lot of them were wrong.
How bad was it?
It was pretty bad because I think their priors are not information theory lectures.
Right. Well, I'm giving them great training data. Yeah. With keywords, not moreover. I mean, they could actually use this as distal training data. Although when I do start saying things like House of Cards, that's not very useful. So in any event, so let's go back to this. So arithmetic coding. So it uses this arithmetic coding. So the other thing I give them is I highlight words. Arithmetic codes. You use a subinterval of 0, 1 corresponding to this distribution. Okay, so it's actually great data for pronoun reference problems, right? Because I'm always saying this distribution, right? So anyway, we have adaptive arithmetic codes. We saw the Dirichlet distribution, the Laplace distribution. The next example we're going to cover is Lempel Ziv. So the idea is entirely algorithmic and seemingly heuristic. And the idea is to memorize strings. And as we'll see, it doesn't actually use the distribution at all. It doesn't even need to have a Dirichlet distribution or a Laplace distribution or some fixed distribution like in Huffman code. It doesn't need to decide beforehand a blocking strategy or a block length. It doesn't need to use the method of types. And it's amazing to me. I hope it will as well to you be amazing that it converges to the entropy rate. Okay, so Huffman is inherently two-pass, right? We choose a length, and this is whenever you run a lot of compression algorithms, say, okay, let's choose a particular block or a particular length of thing. We estimate the distribution over it, and then we do another pass, and we say, okay, each symbol has a certain probability, and then we output bits based on that symbol's probability. We also pay this extra bit per symbol. We need to use a long block length. This is what I mean by the extra bit per symbol. So this is the entropy rate down here, right? And so in order to make it converge to the entropy, we need to make n big, or to make that 1 over n guy go to 0. And what we'd like, and the idea of Kolmogorov complexity, what that suggested in our minds, hopefully, is that if we could, for example, every time we encounter a string, just send its description length, we know that would be as good as the Shannon lengths. We don't have to know the distribution. We can do this universally, irrespective of what do you think Google is going to recognize for those bells, those wonderful bells? What do you think? Anyway, so what's amazing about Kolmogorov complexity is we can just say, here's a string, here's a description length, we know that it converges to the entropy, regardless of what the probability distribution is. We've never needed to estimate it, we've never needed to compute it, we've never needed to even say that there is a distribution, because even if there isn't a distribution, we still have a short description length for that particular string. All we need is this paradigm of a program, of a universal program. So we still want it to be universal in the same sense as Kolmogorov complexity. We want to not necessarily know or acknowledge that there exists or need to estimate or compute in any way, shape, or form some underlying source distribution. Yet at the same time, we still want to be able to prove that when there is a distribution, we can converge to the entropy. Can this be possible, practically? Yes. The answer is yes. And Lempel Ziv does it. And because I think this is an important result, we're going to go through the proofs in detail. Because you might think, how could this be? This is impossible. But oftentimes things that are seemingly impossible are not impossible. I should mention also that, has anyone used gzip? Does anyone know what gzip is? Or bzip? Or zip? I don't know why they're all called zip. That's just the universal sound of compressing, right? When you make something smaller, don't you always just think zip? When you have a trash compactor at home, remember those trash compactors that people used to put in their kitchens? And it would flash zip on it, right? Everybody knows what those are. I remember them.
So like the plain old zip is different algorithm, or it's probably also Lempel Ziv too, right?
Uncle Zip?
Lempel Ziv is probably used for zip.
I believe Lempel Ziv is used for zip. Bzip2 is a little bit different. I mean, it's a similar kind of text algorithm, but sometimes it's better, sometimes it's not better. I think probably on balance, Bzip2 is a little bit better, but not by a significant margin. I still use gzip, just because I'm an old Unix guy, and my fingers can't unlearn gzip. It's just automatic. Okay, so I think this is a good time to take a break then. Okay, what is Lempel Ziv compression? So the idea, let's talk about first the idea. The idea is that source sequence, so we've got a source sequence of symbols, and for the most of the time our source sequence is going to be either binary or there's going to be some alphabet, but most of the time we're going to think of it as just a binary string. But for right now, let's just say we have a sequence, and the sequence is parsed into phrases. So basically we put commas every so often. So normally it's just a bit string, right? Or a string of symbols. There's no punctuation marks. But what we're going to do is put a comma between each of the phrases, and the choice of phrases is determined by where the commas go. And the way that we do this parsing into phrases is that the next phrase is defined to be the shortest one that has not yet been seen. So it's not seen so far, and then in the previous history of all the phrases that we've got. So we keep going, like when we get a next symbol, has it been seen before? Yes. Is it next symbol, have we seen before? Yes. Next symbol, oh, we haven't seen that particular phrase, comma. And that's how we do it. So like for an example, here's the string, this is the thing. So we're just going to parse this string here, right? And so it's the following parse. So the first letter is going to be T, because T is the shortest string that we haven't seen so far. The next one's going to be H, because we haven't seen H yet. Next one's going to be I. Next one's S, because we haven't seen S so far. Next one's going to be space, because space is a character in this particular procedure. Now if we did I, if I was the next phrase, well, I has been seen before, right? So that's not a phrase. The next one, so we have to add an S. But then we say, okay, IS. We have seen IS. Okay, PE, everybody. Don't forget to put on your shoes. Nobody knows what that means. Does anyone know what that means?
I do.
That's a mocking, sardonic comment against the University of Washington's Bell reminder system. So IS has not been seen before because we've seen I, but we haven't seen IS. So that becomes the shortest phrase not yet seen. The next is space. We've seen space, so now we need to add a T. Right, because if we just put a comma after space, that's not the shortest string we've seen so far, because we've seen space so far, so we need to add a T. We haven't seen space T before. We've seen an H before, but not an HE. And we've seen a space before, we've seen a T before, and we've seen a space T before, but we've never seen a space TH before. So that becomes the new shortest string not before seen. And then IN is the next one, and then G, we had never seen a G before, so that's its own phrase. So does everybody get the idea based on this? So this is the parsing. Any questions on this?
You have seen space before, right? With IS space T, right?
In which one?
First space, you have INS together, right? You should have
So
IS space and T together.
This one? It's the shortest phrase not be seen before. Remember? So, yes, IS space has also not been seen before, but IS space is not the shortest. The shortest is just IS. So, critically, it's the shortest phrase that have not been seen before.
I think he's referring to that there's an IS in this. So it only matters if you've seen it before in your parsed list, not if it's
So far in the previous history of phrases.
Yeah.
So you have to get these guys, that guy and this guy. Okay. Any other questions on this? Okay, let's do this binary string. So we're just changing the alphabet. So this gets parsed as following. So let's just do it a little bit. So 1, we've never seen 1 before. It's the first thing. So anything that we start with is always going to be one symbol. And then any unique symbol that we've never seen before is going to also become its own phrase. But now we see a 1. We've seen that before, but we've never seen a 1, 1. So that becomes this, right? And then 1, 1, 1. 0, 1. We've seen a 0 before, but we've never seen a 0, 1. It becomes that guy. And then we've seen 0, 1 before, but we've never seen a 0, 1, 0, so that becomes this guy. We've seen a 0 before by itself, but we've never seen a 0, 0 before. And we've seen a 1 before, but we've never seen a 1, 0 before, and so on and so forth. So that becomes parsing. Okay. So this is just a rephrasing of what we're doing. So I don't know why this is here. But that's basically saying the same thing as this, just to sort of go with the philosophy of telling you what you're going to tell them, and tell them what you told them. So this is the telling you what I'm going to tell you, this is the telling you, and this is the telling you what I've told you. And now this is the telling you what I've told you, what I'm going to tell you, and then what I've told you. This is yet another meta level of that. Okay, so that's all. So basically now when we look at these prefixes, any token that we've seen, any phrase that we've seen, the prefixes up to the very last symbol have always been seen before. So it's the last symbol that makes it unique, thanks to the shortest constraint. But any prefix we've already seen before. For example, like in this guy here, let's take this long one. 0, 1, oops, that's too big. 0, 1 has been seen before. It's been seen before here. And this guy, space 0, space t, has been seen before. So any prefix has always been seen before. It's the last symbol that makes it unique. So it's a unique parsing. Okay. So I thought I had another bullet point here, but now I'm getting confused. Okay, so how do we encode? So to encode this, get rid of that mouse. What's a mouse doing here? Oh, this I could use this as our pointer, couldn't I? I never realized that. But that's not on the iPad. That doesn't count. So how do we encode? So to encode, what we do is we give. So we have this sequence of phrases, and the phrases have a number, like the first phrase, the second phrase, and the third phrase. So what we do is when we want to encode such a string, since all the prefixes of every phrase have seen before, for that prefix that we've seen before, we just give the integer corresponding to that prefix. We just say, oh, that was number 3. Oh, that was number 7. And then we append that integer with that last symbol that makes the new phrase unique. Okay? If it hasn't ever been seen before, we use the special pre-arranged integer 0 as a null pointer, basically. So here's an example of encoding the string. So this is the string, and let's zoom in a little bit on it. So the first symbol is t, right? And so we just go ahead and it's position, which is just counting which position the phrase is. So it's phrase number 1, and we use the null pointer here. Just says, there is no prefix anyway, but it's never been seen before. Next one is h, and also has a prefix. So this basically goes on and on until finally we get to is, right? So is is here, and it says, oh, I've seen the prefix before, I. And so what happens is that this 3 points to this entry. Points to the entry, right? I mean, I guess in some sense you could say it points to this, because what we really want is the prefix. So when we get this, if we wanted to do this, we would say, oh, if we wanted to get this one here, we'd say, oh, let's go back to 3, print out whatever that string is, and then append that with an s. And that's how we get it. Okay. Similarly, for space t, 5 points to this guy, and then we append it with t. And to do this one, you have to zoom out a little bit, but 2 points to this guy, which is h and then e, and then 7 points to this guy, which then, you have these traces going back, but that's okay. You can always go back, and then, this one points to 3. 3 points to this one again, im. So these are pointers, and so we can do this in the binary string case as well. I mean, there's no difference really other than the alphabet. We can do this for any finite alphabet, in fact. And we have the following parse. So any questions about these parses? Why don't I pause? I'll just let everybody digest them for a second. See if you have any questions. So this seems like a good thing, right? I mean, for example, just intuitively, as we proceed, let's say that there is structure into these strings. So there's not, they're not just purely random. So as encoding proceeds, the pointers in general are going to refer back. Well, I should say the phrases are going to have longer and longer prefixes. Right? So if it's the case that the amount of space necessary to store the pointer is less than the prefix itself, which seems like that may be reasonable. In fact, that seems quite likely. because we, in general, to store a number between 1 to n, we need log n bits. So the number of bits to its index is growing rather slowly, but maybe the number of prefixes is growing rather largely. And so it seems like the potential for compression improves because of the prefixes getting longer and longer. And all we're going to be using is just some integer pointer to point back to the prefix and then appending it with a single symbol. English, for example, or any natural language, this seems quite useful for. Like, as soon as you've used an entire word, or as soon as you've used a phrase, like, let's say that you really love the phrase, Constantinople is beautiful in springtime. I don't know, a random phrase. Is it beautiful in springtime? I think it is. But let's say that you love Constantinople is beautiful in springtime. So as soon as you said that, if you ever encounter Constantinople is beautiful in springtime again, you'll just have a pointer back to that entire sentence. And thereby save quite significantly in length. So the question really is, how many bits do we need to refer back into a pointer? And that depends on how many phrases there are in the first place, and depends on having a bound. And so the analysis, as we're going to see, and we're going to spend today and next lecture on, is coming up with these bounds on these quantities. So let's say that C of n, we're going to define C of n to be the number of phrases of the string of length n parsed in this way. Okay. So we're using this type of parsing, and C of n is just going to be our measure of the number of phrases. And so we're going to need, if we, for example, index, if we have an index that can index into the past, we're going to need log cn bits for the pointers. Right? And then it says it's a binary encoding, so we're in the binary world here. Right? So since we're in the binary world, we need one additional bit to describe the final bit. Right? In this binary. Or one character in the general case. But in the binary case, we're going to analyze the binary case. So here's an example where Cn is equal to 7. So we need 3 bits, and so each phrase is then encoded in the following fashion. We have phrase 1, phrase 2, phrase 3, and so on and so forth. So basically, we have these two things. We've got the pointer, which is it's an integer that uses a certain number of bits, and then we have it's not that. We have final number, the final bit. Okay, everybody get it? Everybody got the idea? So how do we decode? Well, decoding is fairly easy. We just keep a table of strings that we've already encountered. Or we could actually do this backtrace kind of thing and trace back to the beginning. But basically, we just keep a table and we index it. We know how big C of n is, and so we allocate an array of size Cn, and then every time we construct a string, we just put that string into the table. And the next time we see a phrase or encoded phrase, we just use the first log Cn bits to index into the table, spit out that string, and then add the final symbol. And so each phrase is going to be unique, right? Each phrase is never going to before be seen, right? So if there's redundancy, we're going to save quite a bit, right? Like, what if we have all zeros? The first one's going to be 0, and then 0, 0, and then 0, 0, 0, and then 0, 0, 0, 0, and so we're going to very quickly essentially be referring back to longer and longer strings. So the question is, when might this work well with low entropy sources? How do we this algorithmic procedure? How do we analyze this and compare it to entropy? If we do have an entropy, we do have a stochastic process of some sort. How do we actually compute this? And so this is the algorithm that's basically used for gzip. So just intuitively, basically, whenever we have lots of repeated strings and substrings, like text, and one of the reasons why it works so well in text, and why it's used, and this algorithm, or this type of algorithm is used for text, is because the assumptions that this algorithm makes are very apropos in standard human text. There might be other low entropy sources where this becomes a little bit tricky. Like if you were to try to run this on just raw sampled audio or something, right? I mean, have you ever noticed that when you take a .wav file and you try to run gzip on it, it doesn't compress? Because it's, in some sense, the alphabet size is so big that you would need to have an extraordinary, what it actually is true that this would compress this ultimately, but you would need an extraordinarily long audio file, longer than a Wagnerian opera, to actually achieve any form of compression with such an algorithm. But ultimately, if it was long enough, possibly longer than the Jurassic era, it would compress. So let's now analyze it. So the rest of today's lecture will be assuming a binary source. But are there any questions on this so far? Yeah. So anyone imagine how we might be able to compare this to entropy? So it's purely heuristic, or seemingly heuristic. Does it compute any probabilities? No. It just like Kolmogorov complexity, it says, okay, here's a string, here's this algorithmic procedure to encode it. Right. The length is going to be the length of whatever bit string it comes out of it. And so somehow what we want to be able to do is show that those lengths are, on average, per symbol, as good as the Shannon lengths. In the same way as we showed that Kolmogorov complexity is, on average, asymptotically as good as the Shannon lengths. But it's very similar to the nature of Kolmogorov complexity, right? Because it's just a function of the string itself, in that it gets to use the identity of the values of x's. It's not based only on the probability. That's a really important point. Like, just like Kolmogorov complexity, it's not saying, oh, I'm going to allocate a number of bits depending on that probability, irrespective of what the content of the string is. This is actually using the content of that string. Does that make sense? No? Okay. Does it make a lot of sense? Raise your hand if it makes a lot of sense. Okay, good. Okay, binary. Let's just define a couple of definitions. So what we're going to call a parsing in this context of a string is basically a division of the string into phrases separated by commas. So any parsing, it doesn't have to be unique, just a parsing of such is basically an insertion of commas between at certain points. And then a distinct parsing is going to be one where no two pairs of phrases are identical. So that, as we saw before, the Lempel Ziv parsing produces a distinct parsing, because remember, we always parse it into the shortest thing never before seen. Right. So remember, the prefix has been seen, but by the definition, we're adding one more symbol to the phrase so that it's not before been seen. And so, as an example, this is a parsing of this string, but it's not a distinct parsing because we see 1 being used twice. This guy and this guy. But on the other hand, if we took the same string and parsed it in this fashion, then it would be basically, it's a distinct parsing. So that's a distinct parsing. This is not a distinct parsing. And as I said, Lempel Ziv produces a distinct parsing. Okay, so like we said before, C of n is just going to be the number of phrases in a parsing of some string. So Cn is really a function of the string. It's not just a function of n. So we're going to use notation in this fashion. So in case it's confusing, we might use C, or we might use Cn, or we might use C of x of 1 through n. But it's really the same number. It's just the number of phrases that Lempel Ziv has parsed the string x of 1 through n into. Okay, the most accurate is this one here, right? So after we've done the compression, we have this sequence of Cn pairs of numbers of the form pointer, comma, bit, where each pointer itself requires log of Cn bits. right? And so we have log of Cn plus 1 bits, and so the underlying length of the compressed sequence is going to be equal to the number of such strings times the number of bits in each string, which is Cn times log Cn plus 1 bits. Right. So how do we show that the Lempel Ziv achieves the entropy rates? And that's what we want to do. That's what we're going to spend, like I said, it's going to take us a while. So our goal, if you will, is to sort of demonstrate this, that the per symbol, the number of bits per symbol of the Lempel Ziv compression scheme, which is on the left, converges to the entropy when you've got a stationary ergodic source. Okay, is the goal clear? Any questions so far?
That means for a sequence of all zeros, we have to use a constant number.
Well, it depends on the entropy, right? Because remember, this is the entropy is a function of a random distribution over strings, right? And so this thing on the left would also, in some sense, need to be random. And so what we're saying is that that converges to that in probability, right? So we need to have a notion of convergence in our class. We've been using convergence in probability. So that basically means that the probability of these two quantities differing by more than epsilon can be made arbitrarily small if the block length is big enough. That's what we really mean. What does it make? What does it mean? I mean, this is something that's an important point, right? So, like, again, let's look at the left-hand side. So, I don't know why I'm putting this down. So, I'm putting it down because I thought I didn't need it, but actually I do need it. So, this left-hand side, we described the process that gives a particular Cn based on one string, right? And it doesn't use the probabilities at all. And so any encoding length, or in this particular case, this is a per symbol encoding length. The algorithm doesn't say, like Huffman, go over the string, compute probabilities, do it again, and produce number of bits based on its probability. Or the arithmetic coding where you have some sort of adaptive algorithm for producing a conditional probability distribution. This is basically saying, oh, I don't care what the probabilities are, just do these pointers. So that basically means for any one string, this left-hand side that I circled in red is the encoding length per symbol. But when we compare it to the entropy, we have to remember that the entropy is a function of a random variable. So maybe to make this clear, if I took if I wrote this as let's do it this way. So I took this as the expected value of, and what is the expected value with respect to? With respect to P of x1 through n of this quantity. So we have C of capital X1 through n, right? It's a function of a random variable times log C capital X1 through n. Oops, what's going on there? Thanks. Oh, I know what's going on. I'm running out of room. Let's move this. This is the beauty of this program. So plus 1 divided by n. Right? So that thing has to converge to the entropy rate. Right? Because remember, Cn in this context is really a random variable. And when you take this function of the random variable, Cn times log of Cn plus 1, expected value with respect to this distribution, which was presumed to exist, if you're computing entropy, there has to be presumed to exist. But the point is, just like the Kolmogorov complexity, remember in the Kolmogorov complexity, we did things like expected value with respect to P of x of K of x. Right? That's what we said was just as good as log of 1 over p. Just like in the entropy case, this encoding length here, which itself is a random variable, but for any given string it's not random. So this guy here, which I'm about to outline, this encoding length doesn't use the probabilities, right? It just uses the context of the string. It's an algorithmic encoding strategy, just like Kolmogorov complexity. But in this particular case, it's practical, right? It's realizable. We can write a computer program for it. We don't need to solve the halting problem for it. There are no deep philosophical implications associated with it. It makes for a much more mundane class lecture than Kolmogorov complexity from the philosophical perspective. But on the other hand, it's very, very practical, and we use it a lot. So does everybody understand this, what we're trying to do, and how we're connecting these two things together? Okay, does everybody know what little o notation is? Let's do a brief review, if you don't. Little o notation? Everybody remember? Does everybody remember? Okay, so I don't have to go over this? Or should I go over it quickly? Little o notation, well, I will go. I see some looks of uncertainty. So little o notation is basically a class of functions. Basically, we say that O of g of n is a set of functions. So it's basically all functions f such that any constant that we want, at some point or another, that function is going to be dominated by that constant times g. Right? So it's all functions that in some sense are dominated by that constant times g for n big enough for any positive constant. And any such function. So basically it means g dominates f eventually. We can make c as small as we want. We can make c 10 to the negative 1 million. And f is still going to be dominated by it eventually when n gets big enough, namely bigger than n naught. There exists some n naught such that it's always dominated by it. So that basically means that it's all functions that are dominated by that guy. Sandwiched above by c of g of n. Maybe dominated is a better word. Usually a sandwich has 2 slices of bread, not 1 slice of bread. Have you ever had a sandwich that has bread and hummus? Talking about, I was just reminded of these terrible hummus sandwiches that you can buy. It's like white, pasty, starchy bread with hummus on it. It's like if you're going to eat a vegetarian sandwich with hummus, why do you give us the worst white bread? They sell us this at our food court in our building. Does anyone actually try one of those? Well, I don't anymore. I did at one point when I'm looking for the vegetarian option, because I usually eat vegetarian. I almost always eat vegetarian, in fact. But the white bread was very disturbing. On one hand, so I scraped off the hummus, ate the hummus, and then tossed the white bread. And that's nice. Actually, I felt like doing that. But anyway, it's not really sandwich because there's not really here. There's like a one slice of bread sandwich. Importantly, so let's just go through this quickly. So this is O of g of n is a set of functions, each of which satisfies this constraint. If we're saying that f is a member of this class, it means that g grows faster than f eventually, right? Or shrinks faster, if you will. I mean, it's basically saying that f is dominated by g eventually. So if g is not 0, if it's not 0, then if f is a member of O of g, it's kind of like saying that the limit of f over g goes to 0, or is equal to 0. Right? Because it's saying for any constant, we can make a constant as small as we want, and that there's always going to be some n. So another one, and the way we're going to use it is O of 1. So O of 1 is used all over the place. You should be very familiar with this. So when you see O of 1, what this really means, just you speak the language, that's asymptotically 0. That's what that means, right? It basically means O of 1 are all these functions that for any constant we want, at some point or another, it's going to be dominated by c, where c can be as small as we want, right? So if you're a member of O of 1, you're going to get really small eventually, as small as we want. In fact, you're going to go to 0. So that basically means equivalently that the limit of f goes to 0. So that's another way of saying that. And so you could say f is a member of O of 1 should see that, then that's 0. That basically means it doesn't matter. So what we're going to see, talking about the O1 notation, and the rest of today's lecture, I think, is going to be this proof. It's going to be basically saying that we can bound the number of phrases. Number of phrases in any distinct parsing, not just the ones produced by Lempel Ziv. In any distinct parsing of a binary sequence satisfies the following. So it's going to be less than or equal to n over log n times 1 minus epsilon, where epsilon is going to be going to 0. So another way of saying this is that this is dominated above by n over log n times a quantity 1 plus O1. And remember, we said O1 is asymptotically like 0, so basically it's kind of like saying it's for all intents and purposes when n gets big, dominated above by n over log n. Okay. First of all, do people see why 29.6 and 29.7 are equivalent?
Taylor expansion.
What's that?
Do the Taylor expansion of 1 over 1 minus epsilon.
Yeah, you could do that. That would be one way of doing it. Taylor expansion of 1 over 1 minus epsilon. You could just subtract it. You know, you could say for example, like 1 over 1 minus epsilon. You know, what is that? It's like 1 over 1 minus epsilon, which is slightly bigger than 1 minus 1 plus 1. So that's the way I would simply do it. If you take 1 over 1 minus epsilon minus 1 plus 1. So this guy, that's going to be O1. Right? So therefore these statements are equivalent. Okay, so first of all, let's then proceed and do this proof, because I said we wanted to go through these proofs, because I think, like I said, well, I'm not going to say it again. I've already said it. So nk is going to be defined as the following quantity. It's going to be the sum of lengths of distinct strings up to length k. Okay. So basically, think of it this way. There are a set of strings of length k, right? They're all distinct from each other, right? As long as there are no repeats. And there's a set of strings of length k minus 1, and as long as there are no repeats, they're all distinct. And a set of strings of length k minus 2, and as long as they're all distinct, there's no repeats. They're all distinct, and so on and so forth. Basically, we're taking all of these strings together, and we're summing up all of their lengths. Okay, so it's 2 to the k plus 2 to the k minus 1 plus 2 to the k plus 2, take k minus 2, and so on and so forth, all the way down to length 1. And then nk is going to be that quantity. And then what we're going to do in order to express this quantity, we're going to say, okay, well, it's the length. We're going to take it as take nk as the sum over length times number of strings of that length. And I should really have this on the other side because it makes a little bit more sense. Now, before we do that, let's just sort of write this quantity. So here, when we make this sum, oops, right here. When we do this, we can just add and subtract 1 in this fashion, right? But now if we sum up for k is equal to 0, for L is equal to 0 to k of 2 to the L, we get 2 to the k plus 1, minus 1, and then another minus 1, we get minus 2. So we get this quantity here. Okay, so everybody hopefully sees this relationship. So that we're going to be then using from this to this in a number of cases. Okay. So starting with nk, so that can be expressed in the following fashion. So again, this is what that bullet point on the previous page that I said should have been on this page says. Is that what it represents is there's the length, which is this guy, and this guy, which is the number of strings of that length. Right, and then we sum up the product of them, and then that gives us nk, which is all of the set of all strings, all distinct strings of length up to and including k. Right? So another way of writing this is in this fashion. Okay. So here what we're doing is just writing it by expressing only the quantity of the sums by starting the index at 2, 3, or 4 up to k. And so therefore we can write this as this double sum. Okay? And the double sum, so we're summing this double sum for j is equal to L to k. We could start it from j is equal to 1 to k minus the stuff that we've overcounted. And so that's what we're doing in this next slide here. So we're summing it from j is equal to 1 to k minus the stuff that we've overcounted in order to get this quantity here, which is this bit here. Everybody see that? Okay, next, what do we do? Next, what we do is we write, we use this guy and this. So we've got something which is only dependent on the upper sum, right? So here, the upper sum is k, so it becomes 2 to the k plus 1. The upper sum is L minus 1, so the upper power becomes L, and then the 2's corresponding to this guy cancel out in the difference here. Okay. This is the real challenge for Google speech recognition, because I'm pointing and saying this. How would it know, based on what's on the screen, that it corresponds to what I'm saying? Okay, so then we can write this in exactly the analogous fashion, where we've got the first term. For this bit here, it's just this is just a constant in this first term, so we just have k versions of it. So that bit just goes there, right? And then the rest of it, like the sum and this stuff here, we apply this formula, and we get minus this whole minus stuff, 2 to the k plus 1 minus 2, which is this spot here. Okay. So then rearranging terms, we've got 2 to the k plus 1 occurring twice. So it's k minus 1 and 2 to the k plus 1 plus 2, which is this one. And that then gives us our expression. Just if anyone has forgotten what we're actually doing, we're coming up with a very simple expression for n sub k. And what's nice about this expression is that it doesn't involve any sums or anything like that. It's just a very simple expression that can be easily manipulated. And so we're going to use this relationship then. Okay, now this is the tricky part. If you're wondering, the part we've done is so far algebraic, but the next part is a little bit tricky to understand. So what we're going to do is we're going to consider different lengths n of the string. Right? So what we're trying to do, remember, is trying to come up with a bound of c of n. So we're going to consider different lengths. In one case, we're going to consider a length where n is equal to nk for some k. So n is exactly equal to nk, where nk is a value which is the sum of all unique strings of length up to and including length k. And then what we're going to do is we're going to consider a case when, okay, suppose n is between nk and nk plus 1. So the first case we're going to do is going to say assume n is equal to nk for some k. And we're going to analyze that case. And then the next thing we're going to do is going to say that assume that nk is less than or equal to n is less than or equal to nk plus 1 for some k. Now we're going to do, of course, this first case first, because that's easier to analyze, and it's going to be necessary to construct a bound on the other thing. But basically, with this information, we're going to be able to come up with interesting relationships associated with C of n, the quantity we're interested in bounding. Okay, so does everybody get what we're doing? So now, remember, so nk, what is nk? nk is the sum of all unique string lengths up to and included length k. If n was equal to n, well, let's just, I think I should just go to it. So the number of distinct phrases, C, in that string is maximized when all phrases are as short as possible. Right? So like if we want to, like the Lempel Ziv, for example, parsing in some sense maximizes C of n, right? And because it always takes the shortest unique string next, right? So it takes the prefix and one more thing to make it unique. But in general, when we have a number of unique strings, there's lots of ways of parsing a string into unique strings, right? But if we wanted to maximize this, we wanted to bound this quantity, upper bound it, then we would make the strings as the unique strings as short as possible, right? But if n is equal to nk, right? So that basically means that the biggest possible value of C, which is basically the number of unique strings, would be basically there being all instances of unique strings up to and including length k. So like I said, this is the tricky part. Okay? So remember what we're doing here. We're saying, okay, suppose, so nk is some quantity, right? What is nk? Nk is the number, is the sum of all unique strings up to and including length k. Right? That's what nk is. And now we're saying, suppose we have some string which is of length equal to the sum of all unique strings up to and including length k. Right? Now we want to say, what's the maximum possible way of parsing n into unique strings? Right? That's what we're going to be doing. So C would be C, the thing that we're trying to bound, is maximized by considering all such distinct strings. So what this is saying is the following. When this is true, when n is equal to when n is of length equal to the sum of all these distinct strings, and here's again our formula. I'm just writing this for convenience. This is something that we need to use. The number of distinct strings of less than or equal to k, namely C of n, which is this thing that we want, is going to be upper bounded by this quantity, right? Now notice that if this is confusing to you, C of n and C of n k happen to be the same, right? Just because we're setting right now n to be equal to nk. Nk is this, and I think I misspoke earlier. So nk, not in the first time. I think once I misspoke. I usually don't misspeak more than once, but nk is the sum of the length of the unique strings up and including k. C of nk is just basically the number of unique strings up and including k. So the number of unique strings of length up to and including length k is going to be this quantity here. That guy, right? Because how many unique strings are there of length 1? Well, there's 2. How many unique strings are there of length 2? There's 4. How many unique strings are there of length 3? There's 8, and so on and so forth. We sum all of those guys up till we get the total number, or at least the upper bound on the number of distinct strings of length less than or equal to k. Okay? So now we can write this in this fashion, right? Using that inequality we did before, which we're once again using, and we can further upper bound this in this fashion, just by getting rid of the 2. But now, let's use this bit. Let's use, you can't, I don't know if you can see that on the screen, but let's use a different color. Let's use this thing. And so with that, we can actually get an upper bound of that C of n is upper bounded by nk over k plus 1. That's just by solving algebraically for this stuff here. But since we've set n, we've assumed in this particular case that n is equal to nk, then that gives us the following relationship. Okay. Okay, so everybody get that. Okay. That's really important. This is I think this is the trickiest bit. So now we're sort of done with the assumption that n is equal to nk. So it's saying that the number of distinct strings, when n is equal to nk, the number of distinct strings of length less than or equal to k is upper bounded by n over k minus 1 when n is equal to nk, which is the sum of lengths of distinct strings less than or equal to k. So the next thing we need to do is we're going to need to say, okay, well, what if n is between nk and nk plus 1? Well, let's come up with a very simple expression for nk plus 1 in terms of nk. So if we take nk, and then we add this quantity here, which we're going to call this guy, this is going to be called delta, and I should have named this on this slide. But we're going to add this delta, okay? It's really delta sub k, so maybe I should give it a k here. So then algebraically we get that this is equal to this. Hopefully that's pretty simple by basically plugging in the definition of this bit here. And then furthermore, algebraically that's equal to this. But then by plugging, also by looking this thing again, we get that that's equal to nk plus 1. So we can go from nk to nk plus 1 pretty easily by adding this delta k here. All right, and remember, what is the definition of nk? Did I hear everybody say it? Nk is the sum of the length of strings up to and including length k. So unique strings up to and including length k. Unique is important. Sum of the lengths of all unique strings up to and including length k. So now there's delta. Now suppose, what we're going to suppose now is that n lies between this bound. And I really, like I said, I should have called this delta sub k. And I'll fix the slides for future. Because it's really dependent on k. Because all deltas are really delta k. Now suppose n is between this. So basically n is, sorry, that's actually, what I just said is completely wrong. I'm forgetting my own slides. So I take back what I said about this being delta. This delta is only n minus nk. Right? So it's basically just this bound. I'm using delta in the wrong way. It's this thing. It's just n minus nk. This is really getting confusing to you, and I apologize for making that mistake about delta. So this value here is this stuff here. This is the gap between nk and nk plus 1. Delta is the gap between nk and n. So let me draw a figure. This will make more sense. I don't do this very often, but let's draw a. There we go. Okay, so what have we got? So there's our line. Okay, so we're starting with this guy, and then this guy. And this point here is going to be just n sub k. And this point here is going to be n sub k plus 1. Right? We have this gap. So we have the gap between nk and nk plus 1, but what we're doing is we're placing n right here.
So nk is still 2 to the k minus 2.
Oops.
Right?
Nk is always going to
2
be...
to the k minus 2.
Let's go back and make sure that we have this right. So nk
C of nk
is going to be... The C of nk is we're basically bounding C of nk. Okay? But what we want to do is bound C... What we have right now, what we've done in equation 21.11, is we've bounded C of nk for any n such that there exists a k where n is equal to nk. But those are only these sort of narrow points, right? So that's only for these points. So So we've got this guy covered, and we've got this guy covered, but what about all this stuff in between? We need to have a bound for C of n for all the points in between. So we've already got these green ones covered. Now what we need to do is come up with a bound for C of n when n lies in between. And so what we're calling delta is this thing. Delta is the gap. So what I said initially about delta was not correct. What I said initially was delta is that delta was this value. But that's not delta. This is something else. This is a gap, which is equal to nk plus 1 minus nk. Okay, and you remember what that gap is. That's basically listed. That gap is this guy here. K plus 1, 2 to the k plus 1. Right. So delta is at most equal to k plus 1 times 2 to the k plus 1 minus 1. So again, we want to bound, remember, we're trying to come up with an upper bound of C of n, is less than equal to something. Right? And so we've got these green points covered. Now this is a really bad time to end. I was hoping to finish this proof. Shoot. Okay, does everybody get the idea of what we're doing? First we're bounding C of n for those points where n is equal to nk for some k, then we're bounding C of n for those n's that lie between nk and nk plus 1. And delta is this gap here. Okay, so when we have this gap, we might get kicked out of the room. This is, yeah, I'm going to have to rush through this if I do this. We're going to have to finish this next time. I apologize if this went too slowly. Raise your hand if this was too slow. Raise your hand if this was too fast. Raise your hand if it was just right. Okay, that's very good, because it basically, first of all, you tell me this, I don't know if it's really true, because I only would believe it if it was anonymous. But we will continue this proof about a week from today. That's a long time to break a proof into two pieces. This was bad planning on my part. However, on YouTube, if you're watching this 100 years from now on YouTube, you will have zero gap. And so for you YouTube listeners out there, 100 years into the future, you have, I don't have any, I don't feel sorry for you at all. You lucky ones from the future. What's life like in the future, I wonder?
They should donate to the University of Washington.
Through a time machine, right? Because remember, they're living 100 years from now. They're living 100 or 1,000 years from now. Maybe they'll still be watching this 1,000 years from now. Okay, anyway, see you guys on Wednesday, and bye.